Hello students, welcome to this lecture on linear prediction of signals. Let us recall, we discussed the FIR and IR Wiener filters in the last lectures. FIR Wiener filter, where estimator is given by summation hi yn minus I going from 0 to m minus 1. Non-causal IIR Wiener filter, where the estimator is given by summation hi yn minus I going from minus infinity to plus infinity. And the causal IIR Wiener filter, x at n is given by summation hi into yn minus I going from 0 to infinity. Applying the orthogonality principle, we got the Wiener-Hoff equations in each case. We solved the Wiener-Hoff equations by matrix inversion in the case of FIR Wiener filter. In the transform domain, in the case of non-causal IIR Wiener filter, by this equation Hz is equal to Sxyz divided by Syz, where Sxyz is the cross power spectral density of this data and the unknown signal, and Syz is the power spectral density of the data. In the case of causal IIR Wiener filter, we factored Syz, that is the power spectrum of the data, as Syz is equal to sigma v square into Hcz into Hc z inverse, and applied a whitening filter 1 by Hcz, this Hcz here 1 by Hcz to generate the innovation process Vn. We designed the causal IIR filter with respect to this innovation sequence. This lecture will explore one important application of FIR Wiener filter for the linear prediction of signals. First, let us see what is a prediction problem. Given the observation yn minus 1, yn minus 2, etc. up to yn minus m, what is the best prediction for yn? That means, we have signal at n minus 1, n minus 2, n minus 3, etc. up to some n minus m, then what is the best prediction for the signal at instant n? So, we want to predict yn. Now, considering the observations yn minus 1, yn minus 2 up to yn minus m as random variables, the problem is to find the best prediction of yn given yn minus 1 is equal to small yn minus 1, these are the values, yn minus 2 is equal to small yn minus 2, like that yn minus m equal to small yn minus m. These are the given values, and given these values, what is the best prediction for yn? So, we have to find out the best prediction for yn. This is the optimal prediction problem. Now, here we have used one step prediction. Instead of one step prediction, we may have multiple step prediction. Let us see how we can apply MMSE and LMMSE criteria. If the MMSE criterion is used, then the best prediction is given by the conditional expectation. Y hat n is equal to conditional expectation of yn given yn minus 1 is equal to small yn minus 1, yn minus 2 is equal to small yn minus 2, etc., etc., and up to yn minus m is equal to small yn minus m. These are the values of the corresponding random variables. So, this conditional expectation is computationally complex operation, because we have to find out the conditional PDF for conditional PMF, and after that only we can find out the conditional expectation. So, we need a simpler solution. For that we consider linear prediction. In linear prediction LP, y hat n is assumed to be a linear function of the past data. So, just like in the other cases of Wiener filter, we assume that y hat n is a linear function of the past data. So, y hat n is equal to summation h I into y n minus I going from 1 to m, where h I going from 1 to m are the prediction coefficients and m is the prediction order. So, this is the linear predictor. Now, we can apply the linear minimum mean square error principle to estimate the HI parameters. We will introduce the prediction error filter and the reconstruction filter. We have the prediction error given by En is equal to yn minus y hat n, and y hat n we can write like summation hi into yn minus I going from 1 to m. So, that way En is equal to yn minus summation hi into yn minus I going from 1 to m. En is the output of a filter called the prediction error filter. So, this is En is the output of a filter called the prediction error filter with yn as the input. Thus, the prediction error filter is an FIR filter with the coefficients given by 1, this is the 1 minus h1, first coefficient will be minus h1 like that up to minus hm. So, these are the filter coefficients of the prediction error filter. And the transfer function hz we can write in the transform domain, hz is equal to 1 minus h1 z to the power minus 1 minus h2 into z to the power minus 2 etc. up to minus hm into z to the power minus m. So, that way yn is the input to a prediction error filter and prediction error En is the output. We can reconstruct yn from the error signal En by using the inverse filter 1 by hz. So, if I put En as the input, then this 1 by hz will be the filter transfer function and correspondingly I will get yn as the output. So, that way En input to a filter 1 by hz we will get yn. This is the reconstruction filter. The IIR filter 1 by hz is required to be stable. So, that way we have to impose condition of hz so that 1 by hz is stable. Linear prediction reconstruction. Let us see how we can reconstruct this signal. Given En, the reconstruction yn is given by yn equal to summation hi yn minus I going from 1 to m plus En. This is the reconstruction filter. Note that the above equation is similar to an ARM process, because ARM process also we got that. Suppose yn is an ARM process, then yn is equal to summation ai yn minus I going from 1 to m plus Vn. So, that way this equation and this equation are structurally same. For an exact ARM process yn, the linear prediction model of order m and the corresponding AR model have the same parameters that we can show. For other signal, LP model gives an approximation. So, LP model gives an approximation of the signal so that we can determine the error En. And now, we have to minimize the mean square prediction error E of E square n, which is equal to E of yn minus summation hi into yn minus I going from 1 to m whole square with respect to the hi parameters. The linear minimum mean square error estimates for the prediction parameters are obtained by applying the orthogonality condition. Error is orthogonal to data. Therefore, E of En into yn minus j is equal to 0 for j is equal to 1, 2 up to m. And now we can write En as yn minus summation hi into yn minus I going from 1 to m. So, E of this expression into yn minus j will be equal to 0 for j is equal to 1, 2 up to m. By applying the orthogonality condition, we get this expression. And if we take the expectation, we will get ryj minus summation hi into ryj minus I going from 1 to m, and that must be equal to 0. So, which will give you ry of j will be equal to summation hi into ryj minus I going from 1 to m, and we will have m equations corresponding to j is equal to 1, 2 up to m. The above set of equations are the Wiener equations for the linear prediction problem, and same as the Ewell-Walker equation corresponding to ARM process, because in ARM process also we got the Ewell-Walker equations like this. Ry of j is equal to summation hi into ry j minus I going from 1 to m. The m equations can be represented in the matrix form like this. This is the Ry matrix multiplied by this is the column vector comprising of H1, H2 up to Hm, and this product must be equal to the autocorrelation vector Ry1, Ry2 up to Rym. So, this is the matrix form of the equation. Ryj is equal to summation hi into Ryj minus I going from 1 to m for j is equal to 1 up to m. So, this set of equation we can write in the matrix form like this. If we said this matrix Ry as the autocorrelation matrix and small ry is the autocorrelation vector Ry1, Ry2 up to Rym, then we can write Ry into H vector is equal to small ry. This is the small ry, which means that H is equal to Ry inverse into smaller y. So, this is the prediction coefficients which we obtain by inverting the autocorrelation matrix and then multiplying with smaller y vector. We observe that this Ry matrix has a special nature. If we consider the diagonal elements, all these diagonal elements will be Ry0. Similarly, if we examine the first super diagonal, then we will see that all its elements are Ry1. Similarly, here also we will get all elements along the subdiagonal will be Ry1, etc. So, this type of matrix is known as Topliss matrix. Moreover, this matrix is symmetric because autocorrelation function is symmetric. Because of that, this matrix is also symmetric and Topliss matrix. We will develop a fast algorithm to solve the Ewell-Walker equations exploiting this symmetrical Topliss matrix property. We have to find out the minimum mean square prediction error MMSPE, which will be given by E of E square n, that is equal to E of En into, now 1 En we are writing in terms of the prediction error. So, E of En into Yn minus summation hi into Yn minus I going from 1 to m. Now, error is orthogonal to this estimator. Therefore, we will simply have E of En into Yn. And now substituting En equal to yn minus summation hi into yn minus I going from 1 to m, we will get E of square n equal to E of yn minus summation hi into yn minus I going from 1 to m into yn. And this, when we simplify, we will get ry of 0 minus summation hi into ry I going from 1 to m. Therefore, minimum mean square prediction error is equal to ry 0 minus summation hi into ry I going from 1 to m. This is the expression for minimum mean square prediction error. Let us consider one example. Find the second order predictor for yn. Given yn is equal to xn plus vn, where vn is a zero mean white noise with variance 1 and uncorrelated with xn, and xn is equal to 0.8 xn minus 1 plus wn, where wn is a zero mean white noise with variance 0.68. So, we have to find out the second order linear predictor. The linear predictor is given by y hat n is equal to h1 into y n minus 1 plus h2 into y n minus 2. So, this is the second order predictor. We have to find h1 and h2. The corresponding Euler equations are ry0, ry1, ry1, ry0. This is the autocorrelation matrix multiplied by h1, h2. This is the coefficient vector is equal to ry1, ry2. This is the autocorrelation vector. So, this is the Euler equation for the second order linear predictor. Now, to find out ry0, because here we have to find out ry0, ry1, ry1 and this ry0. So, that way to find out ry0, ry1 and ry2, we consider this yn is equal to xn plus vn model, taking the autocorrelation as we showed earlier. Rym will be equal to rx of m plus delta m, and from xn is equal to 0.8 xn minus 1 plus wn, we will get rx of m is equal to 0.68 divided by 1 minus 0.8 square into 0.8 to the power mod of m, and this, if I simplify this, it will be equal to 1.89 into 0.8 to the power mod of m. Now, from this relationship, rym is equal to rxm plus delta m. For m is equal to 0, we will get ry 0 is equal to 2.89 and ry 1 will be equal to 1.51 and ry of 2 will be equal to 1.21. This, using this relationship and this expression, we can find out these values of ry0, ry1 and ry2. So, we have found out these values ry0, ry1, ry1, ry0 and this side also ry1, ry2. So, all these values are known, therefore, we can find out h1, h2 by inverting this matrix and then multiplying with this vector. So, that way we will get h1 is equal to 0.4178 and h2 is equal to 0.2004, and the minimum mean square prediction error will be given by ry0 minus h1 into ry1 minus h2 into ry2. So, all these values are known. If we substitute, we will get that MMSP will be equal to 2.0166. So, that way we got the linear predictor and the corresponding mean square error of prediction. Linear prediction has wide applications. For example, it is used in speech modeling, low bitrate speech coding, that is compression, speech recognition, spectral estimation, DPCM coding, internet traffic prediction, etc. Many prediction problem we can apply linear prediction. LPC10 is the popular linear prediction model used for speech coding. For a frame of speech samples, the prediction parameters are estimated and coded. Instead of coding the raw data, the prediction parameters are estimated and then coded. I will give one example. Suppose this is the original signal, and if I apply LPC and predict the signal using linear prediction, then the predicted signal will look like this. It is almost similar, and the corresponding error we can estimate, and the error will have a very low dynamic range. For example, it is between minus 0.05 to plus 0.05, whereas this signal is from minus 1 to 1. So, that way this is a very small amplitude signal which can be quantized with less number of bits. So, I will give the basic procedure of LPC in data compression. Given a block of data yn, n is equal to 0 to capital N, and the prediction order m, estimate the autocorrelation function from data ry j going from 0 to m, solve the Euler-Walker equations to get hi. We know the Euler-Walker equation corresponding to mth order linear prediction. So, that we have to solve. Estimate the prediction error for n is equal to 1 up to n using the formula En is equal to yn minus summation hi into yn minus I going from 1 to m. Once we have hi's, we can find out the predictor error signal. Now, because it is a linear prediction, so one sample must be there from where we can predict. Therefore, that y0 will be as it is. We have to quantize y0 and hi for I is equal to 1 to up to m at a high bit rate. So, y0, that is the initial sample which will be needed to reconstruct the signal, and hi, filter coefficient, these are coded with a high bit rate. Whereas En, which has a small range, En is coded with a low bit rate. At the decoder, we will reconstruct Yn from the dequantized values of y0's, hi's and the errors using the LP reconstruction formula that we know. Yn is equal to summation hi into yn minus I plus En I going from 1 to m. So, if we use this formula, we can reconstruct the Yn sequence. So, this is the basic outline of the LPC coding. There is an LPC codec CELP, codebook excited linear prediction, where the prediction error En is equal to yn minus y hat n is vector quantized and transmitted. So, in addition to coding the hi's and initial values of the signal, the error part we have to code it, but in the case of CELP, it is coded using a vector quantizer which can compress more than a scalar quantizer. Let us summarize the lecture. In linear prediction, the prediction y hat n is assumed to be a linear function of the past data. Y hat n is equal to summation hi into yn minus I going from 1 to m. The prediction error is given by En, that is equal to yn minus summation hi into yn minus I going from 1 to m. The prediction error filter is an FIR filter with the coefficients 1 corresponding to this 1, minus h1 corresponding to the first term minus h1, minus h2 etc. up to minus hm, and the corresponding transfer function will be given by 1 minus h1 into z to the power minus 1 minus h2 into z to the power minus 2 etc. up to hm into z to the power minus m. This is the transfer function of the prediction error filter. And once we have Hz, we can use 1 by Hz as the reconstruction filter. This inverse filter is used to reconstruct Yn from the error sequence En. For the linear prediction problem, the Wiener equations are given by this. Ry of j is equal to summation hi into Ry j minus I going from 1 to n. This is for j is equal to 1 up to m. So, in the matrix notation I can write like this. So, this Ry of j that brought to the right hand side. So, that way this column will be Ryj, Ry1, Ry2 up to Rym, and this is the m by m autocorrelation matrix. Therefore, in the matrix notation we will have this matrix into the coefficient vector is equal to the autocorrelation vector, and we can solve this problem by applying the inverse transform. So, Ry inverse into this Ry vector will give us H1, H2 up to Hn. The mean square prediction error is given by MMSPE, that is equal to Ry of 0 minus summation Hi into Ryi, I going from 1 to m. This is the mean square prediction error. Please try to answer the following questions. Why are the Wiener equations for the mth order linear predictor and the Ewell-Walker equations for an ARM process same? What are the predictor error filter coefficients to predict an ARM signal? Why should the zeros of the predictor error filter lie inside the unit circle? So, this question also you try to answer. Thank you.